Let us begin slowly and set the mood for what follows. In linear algebra, we often have two parallel stories running at once. One story is geometric and conceptual. It is about spaces, directions, planes, and high-dimensional analogues, and about functions that treat those spaces in a very structured way. The other story is computational and concrete. It is about arrays of numbers, and about procedures that allow us to actually find answers. Matrices lie right at the meeting point of these two stories. A matrix is not, in the deepest sense, the thing itself. A matrix is a way of writing down a linear transformation once we have decided on coordinates. And coordinates, as you know, come from a choice of bases. So, a matrix is best thought of as a linear map written in coordinates, and the particular matrix we write depends on the bases we chose. It is worth repeating already, because we will return to it many times. A matrix is a representation, a coordinate description, of something more conceptual, namely a linear map. If we change the coordinates, we change the matrix, even when the underlying linear map has not changed at all. And this is common, in a way, because it tells us what to trust. We trust the geometric meaning. We use the matrix as a tool to access that meaning. With that in mind, we can move gently into our first section. A linear map takes vectors as inputs and returns vectors as outputs, and it does so in a way that respects addition and scaling. That is the heart of linearity. But to compute with a linear map, we need a way to describe the input and the output concretely. So we choose a basis in the input space and a basis in the output space. A basis is simply a set of directions that allows us to describe any vector uniquely by listing its coordinates in those directions. Once that choice is made, every vector becomes a list of numbers, the coordinates in that basis. Now a linear map can be understood as a machine that turns one vector into another. In coordinates, it becomes a machine that turns one list of numbers into another list of numbers. The matrix is precisely the object that records how the map acts on the basis vectors expressed in the output basis. Let us say this again, slowly and in a slightly different way. To build the matrix of a linear map, we feed the map each basis vector of the input space, one at a time. Each output is a vector in the output space. Then we express each output vector in the output basis, which produces a coordinate list. We assemble those coordinate lists into the columns of a matrix. That assembled array is the matrix representation of the map with respect to those chosen base. So the matrix is not mysterious. It is simply a record, a bookkeeping device that remembers what the map does to the basis directions. It is worth pausing and reflecting on the dependence on bases. If we change the input basis, we are changing the coordinate description of the same input vectors. If we change the output basis, we are changing how we describe the outputs. Either change will alter the numbers we write down. So the matrix depends on the coordinate systems we have chosen. But their underlying linear map does not depend on coordinates. It is the same geometric action. This is an important mental habit. Whenever you see a matrix, quietly ask yourself, what linear map is being represented here and with respect to which basis? And now let us connect this to the most famous operation involving matrices, multiplication. Matrix multiplication is best understood through the idea of composition of linear maps. First you do one action, then you do another. And that leads us naturally to the next section. Matrix multiplication can seem at first encounter like an arbitrary rule. You take rows from one matrix, columns from the other, you combine them in a certain systematic way, and you produce a new matrix. It can feel like a ritual. But the definition is not arbitrary. It is forced by the meaning we want matrix multiplication to have. We want the product of two matrices to represent the composition of the two corresponding linear maps. In other words, if one matrix represents the first linear transformation, and another matrix represents the second, then their product should represent due the first, then due the second. Let us slow down and state that in a soothing, repetitive way. Matrix multiplication is defined so that multiplying matrices corresponds to composing linear maps. The reason we multiply in that specific row and column way is because that is exactly what you get when you track what happens to coordinates when one linear map is followed by another. Now, the most important conceptual point here is that order matters. If you first apply one transformation and then apply another, that is usually different from applying them in the opposite order. Rotations and projections, for example, do not generally commute. Even simple shears in the plane often do not commute. Composition order matters, so matrix multiplication order matters. So, when you write the product of two matrices, you should hear it as a sentence. Apply the right matrix first, then apply the left matrix. It is worth repeating because many learners reverse it in their heads. The matrix closest to the vector acts first. Then the next matrix acts on the result. That is why order matters. Now let us also bring in a gentle but very practical tool for staying grounded: dimension checking. Even if you drift in and out of focus, dimension checking can guide you back. A matrix represents a linear map from an input space to an output space. So it has an input dimension and an output dimension. If one matrix represents a map that takes vectors of a certain length and outputs vectors of another length, and a second matrix represents a map that takes vectors of some length and outputs vectors of some length, then you can only compose them if the output length of the first matches the input length of the second. This is why, for matrix multiplication, the inner dimensions must match. It is not a random rule. It is a condition for composition to make sense. Let us say it once more, in words rather than in symbols. You can multiply two matrices in the order of first this, then that only if the first action produces outputs that the second action knows how to accept as inputs. And when it does make sense, the resulting product matrix represents the combined action. So, the ritual of multiplication is actually just the coordinate expression of a very natural idea, doing one linear action, then doing another. Now that we have a common understanding of matrices as actions, and multiplication as composing actions, we can transition into the place where most people first feel the power of matrices, solving systems of linear equations. A system of linear equations is a set of linear constraints on an unknown vector. You can think of it algebraically as several linear equations in several unknowns. But you can also think of it geometrically as the intersection of certain geometric objects. Each linear equation, in a space of several variables, describes a hyperplane. In 2 dimensions it is a line. In 3 dimensions it is a plane. In higher dimensions it is still a flat object, a hyperplane. So a system of linear equations asks which points lie on all of these hyperplanes at the same time. In other words, what is the intersection of these hyperplanes? This geometric picture is deeply soothing, because it gives meaning to the possible outcomes. There are only a few broad possibilities. One possibility is that the hyperplanes have no point in common. Then the system is inconsistent. There is no solution. The constraints contradict each other. Another possibility is that there is exactly one point in common. Then the solution is unique. A third possibility is that there are infinitely many points in common. Then there is not a single solution, but a whole family of solutions. Often that family forms a line, or a plane, or a high-dimensional affine subspace. Let us pause and reflect. Consistency means there is at least one solution, meaning the intersection is not empty. Uniqueness means there is exactly one solution, meaning the intersection is a single point. Degrees of freedom appear when the intersection is larger, when some directions remain unconstrained. Now, how does this connect to the earlier ideas of subspaces and spans? It is worth returning to a basic principle. The set of solutions to a homogeneous system, meaning a system where the right side is all zeros, is always a subspace. It contains the zero vector. It is closed under addition, and it is closed under scaling. In fact, it is the kernel of the associated linear map. The set of solutions to a non-homogeneous system, meaning the right side is not all zeros, is either empty, or it is a shifted version of that kernel. It is an affine subspace. You take one particular solution, and you add every vector from the homogeneous solution space. So even when we talk about solving equations, we are really doing geometry in disguise. We are describing intersections, and we are describing subspaces in shifted subspaces. Now, the question becomes, how do we actually find these solutions in practice? How do we determine whether the system is consistent, whether it has a unique solution, and how many degrees of freedom it has? That brings us gently into elimination. Gaussian elimination is one of the central algorithms of linear algebra, and it is easy to treat it as a set of mechanical steps. But for tonight, we want to treat it as a conceptual process that happens to be computable. The goal is to transform the system into a simpler system with exactly the same solution set. That phrase is crucial, the same solution set. Row operations are safe transformations. They do not change which vectors solve the system. They only change the way the constraints are written. Let us list the safe operations in common words. You may swap two equations. That clearly does not change the set of common solutions, because it merely changes the order in which you list the constraints. You may multiply an equation by a non-zero scalar. That does not change its solution set, because it represents the same hyperplane described with a different scaling. And you may replace one equation by itself plus a scalar multiple of another equation. This also keeps the same common solution set, because it is essentially combining constraints in a reversible way. So Gaussian elimination is a disciplined sequence of these safe steps designed to expose the structure of the system. As you perform elimination, you look for pivot positions. A pivot is the leading non-zero entry in a row once the system has been simplified. Conceptually, a pivot corresponds to a variable that is determined by the constraints, rather than free to vary. When you reach a row-reduced form, some variables correspond to pivot columns. Those are the dependent variables. Other variables correspond to columns without pivots. Those are free variables. They represent degrees of freedom. It is worth repeating, pivot variables are pinned down by the equations. Free variables can be chosen, and then the pivot variables adjust accordingly. And that is exactly how infinite families of solutions appear. When there is at least one free variable, you can choose it in many ways, and each choice gives a solution. Now let us connect this gently back to the geometry. When a system has a unique solution, the hyperplanes intersect at exactly one point. In elimination language, every variable ends up being a pivot variable. No freedom remains. When a system has infinitely many solutions, the intersection has positive dimension. In elimination language, at least one variable is free. When a system has no solution, elimination reveals a contradiction. You end up with an equation that says something impossible, like a statement that a non-zero constant must equal zero. Geometrically, this means the hyperplanes do not share a common point. Let us pause and reflect again. Gaussian elimination is not merely computation. It is a method for revealing the structure of a linear map and its constraint. The computation supports their understanding, not the other way around. It is worth repeating, the computation supports understanding, not the other way around. Now, one particularly important case is when the system is of the form a matrix times an unknown vector equals a given output vector. In that setting, elimination becomes a way of asking whether the matrix action can be reversed. And that leads us into inverses. Consider the problem of finding an input vector that, when acted on by a given matrix, produces a given output vector. This is the problem of solving a linear system in matrix form. The central question is, does every output come from an input? And if so, is that input unique? Invertibility is a situation where the answer is as perfect as possible. A matrix is invertible when every output vector in the target space comes from exactly one input vector in the domain space. Let us say that again in a slightly different way. Invertibility means the linear map is both onto and one-to-one. It hits every possible output, and it never sends two different inputs to the same output. In still other words, invertibility means there is no information loss. Nothing collapses. No direction in the input space gets flattened into nothing, and no two distinct inputs are merged into one output. Now, how does elimination detect invertibility? When you perform elimination on the matrix, you watch the pivot structure. For a square matrix, invertibility corresponds to having a pivot in every column, and equivalently a pivot in every row. In plain language, every variable becomes a pivot variable, and there are no free variables in the homogeneous system. This is worth repeating because it is one of the most practical criteria in linear algebra. A square matrix is invertible exactly when elimination finds full pivot structure, meaning no row becomes entirely zero in a way that signals dependence, and no column is left without a pivot. The map is reversible exactly when elimination shows there is no hidden redundancy and no missing direction. And this connects back to the equation solving story. If the matrix is invertible, then for every right-hand side vector there is exactly one solution. The system is always consistent and always uniquely solvable. If the matrix is not invertible, then at least one of two things happens. Either some outputs cannot be achieved at all, so some systems are inconsistent. Or some outputs can be achieved in more than one way, so some systems have infinitely many solutions. And often both phenomena occur, depending on the right-hand side. So invertibility is a statement about the behavior of the map as a whole, not just about one particular system. Now, the word inverse refers to the linear map that undoes the original map. If you apply the matrix and then apply its inverse, you get back exactly where you started. And if you apply the inverse first and then apply the matrix, again you get back exactly where you started. This is the algebraic expression of reversibility. But it is worth holding on to the intuitive phrasing, the inverse exists exactly when there is no information loss. Now we can move into a concept that is often taught as a computational gadget, but is far more illuminating when treated geometrically, the determinant. The determinant is often introduced as a number you compute from a square matrix. Many students experience it as a complicated recipe involving expansions or permutations, and it can feel disconnected from everything else. But the determinant has a calm and beautiful geometric meaning. A linear map takes shapes to shapes. In particular, it takes a unit cube, meaning the simplest box determined by the basis directions, and it sends it to some parallelepiped-shaped region, a skew box. The determinant tells you the factor by which volumes are scaled under the linear map. If the determinant has magnitude greater than 1, volumes are expanded. If the magnitude is between 0 and 1, volumes are shrunk. If the determinant is 0, volumes collapse completely into a low-dimensional object. And the sign of the determinant tells you about orientation. A positive sign means the map preserves orientation. A negative sign means it reverses orientation, like a reflection that flips left and right. Let us restate this gently. The determinant measures how the map scales volume, and it also records whether the map flips orientation. It is not merely a number, it is a summary of a global geometric behavior. Now connect this to invertibility, because the connection is deep and worth repeating. If the determinant is 0, then some volume collapses. A three-dimensional region might be flattened into a plane, or a plane might be flattened into a line, or a line might be flattened into a point. In any case, information is lost. And if information is lost, the map cannot be inverted. There is no way to recover the original input uniquely from the output. So determinant 0 corresponds to not invertible. If the determinant is non-zero, then volume does not collapse. No dimension is completely flattened away. The map is, in a precise sense, full-dimensional, and that aligns with the idea that the map is invertible. So, determinant non-zero corresponds to invertible. It is worth pausing and reflecting on how this ties back to elimination. Elimination reveals whether pivots exist in every direction. Determinant reveals whether the map preserves volume in a non-degenerate way. Both are detecting the same underlying phenomenon, whether the columns of the matrix are linearly independent, whether the map is reversible, whether it loses information. And this ties back yet again to the geometry of linear systems. If the determinant is non-zero, then for every right-hand side there is exactly one solution. The system has a single intersection point. If the determinant is 0, then either there is no intersection for some right-hand sides, or a whole family of intersections for others. So the determinant serves as a compact indicator of the nature of solutions. Now, because we are focusing on meaning rather than computation, let us hold on to the interpretive statements. Determinant magnitude tells you volume scaling. Determinant sign tells you orientation, preservation, or reversal. Determinant 0 tells you collapse, dependence, and non-invertibility. Determinant non-zero tells you no collapse, independence, and invertibility. And we can let the computational recipes be secondary, as tools for obtaining the number once the meaning is clear. Let us end by gathering the threads in a calm, unhurried way. We began with the idea that matrices are not the essence of linear algebra, but rather a coordinate language for linear maps. A matrix is a linear action written in coordinates, and it depends on the bases we choose. The same underlying map can look different as a matrix when we change coordinate systems, but the geometric action remains the same. We then turned to matrix multiplication and reminded ourselves that it is defined to represent composition. Multiply matrices because you want to apply one linear action and then another. The order matters because composition order matters, and even the basic dimension rules are simply the statement that the outputs of one action must fit the inputs of the next. From there we moved to systems of linear equations, and we allowed ourselves to see them as intersections of hyperplanes. Solutions can be absent, unique, or infinite in number, and these outcomes correspond to consistency, uniqueness, and degrees of freedom. The language of subspaces appears naturally. Homogeneous solutions form a subspace, and non-homogeneous solutions are either empty or a shifted version of that subspace. We then rested in Gaussian elimination, seeing it as a sequence of safe transformations that preserve the solution set while revealing structure. Pivot positions indicate determined directions, and free variables indicate remaining freedom. We repeated, gently, that computation is in service of understanding, not a replacement for it. We connected this to inverses by focusing on reversibility. Invertibility means every output comes from exactly one input, meaning no information loss. Elimination detects this through a full set of pivots, and the behavior of solutions becomes perfectly stable. Every right-hand side gives exactly one solution. Finally, we approach determinants through their geometric meaning. The determinant measures volume scaling, and its sign records orientation. When the determinant is 0, volume collapses and the map cannot be inverted. When the determinant is non-zero, there is no collapse and the map is reversible. And so, in a quiet way, everything is linked. Matrices are coordinate expressions of linear maps. Multiplication is composition of maps. Linear systems are questions about intersections in images. Elimination is the method that exposes structure without changing meaning. Invertibility is the absence of information loss. And the determinant is a single number that whispers where the collapse occurs and how volumes are scaled when it does not. Let us pause one last time and let that unity settle, one subject told in several voices, all describing the same congeometry of linear action.